All right, today I'm going to introduce you to singularity functions, and there are three of them that I'm going to introduce today. Unit step, which is equal to u of t minus t naught. T naught is going to be a beginning time. It could potentially be 0. The unit impulse, which is defined as delta t minus t naught. That's a small Greek letter delta right there. And unit ramp, which is r t minus t naught. Now, a singularity function is a mathematical function, and it's discontinuous, and it contains singularities. Mathematically speaking, a singularity is where something becomes undefined. Here's an example. Let's say we've got some voltage versus time, and the voltage is 0 over here, but then suddenly it jumps up and becomes a different value, at a higher value there. Right in this region, that's a discontinuity in the function itself, so the derivative of that is going to be undefined at that point. So that's an example of a discontinuous function that contains a singularity there. Okay, let's start with the unit step function. So, unit step. And the unit step, like I said, is written this way. It is t minus u of t minus t naught. And it is defined as either being 0 or 1. It's one of those two values. And it is 0 if t is less than t naught. And it is 1 if t is greater than t naught. Okay, so the unit step, if you were to graph something like that, let's say this is u of t right there, and this is t, then at, this is 0 time, so at some time t naught, it's 0, 0, 0, 0, until it reaches t naught, in which case then it rises up and levels off and becomes 1. Okay, so that's kind of what it looks like. The usefulness of this has to do with what we will use them for in something like a voltage function. So let's say we've got some voltage that's going to be a function of time. Well, we might want that to be either equal to 0, maybe it's 0 before t less than t naught, or then maybe it becomes, let's say, 25 volts for t greater than t naught. And t naught could be 0 here. All right, well, the way you would write that, sort of a shorthand way, is v of t is equal to 25 u of t minus t naught volts, like that. Okay, now schematically, it might look something like this. Let's say the voltage source has terminals here. These are terminals A and terminal B. Well, you might write that as 25 u t minus t naught volts, like that. Okay, so you would see it like that. That's the same thing as doing this. Here's our voltage source. That's 25 volts. And going over here to like a switch. And here's terminals A and terminal B. Well, the switch is, let's say it's originally, I don't know, let's make the switch over here before t equals 0. And, oh, I put the switch on the wrong side. I can't do that. Can't go there. The switch has to pivot at this point and go down this way so that it rotates in that direction at t equals t naught. And again, t naught could be 0. So the switch is down here originally. In other words, there's no voltage across A and B, but then when it's flipped up, suddenly it's connected to this voltage source, and we have a potential difference of 25 volts across the terminals, across A and B. Okay, that's the singularity function. That is the unit step function. It's called a unit step because it has one unit. It's 1. You can multiply it by a factor to change that, so there might be a coefficient out front every time you see that. All right. The next one, let's go ahead and start using the backs of these. The next one is called the unit impulse. Sometimes this one, I've heard it called, especially in physics, is called a delta function. Or sometimes called the Dirac delta. It is defined this way. Let's say delta of t. Instead of writing t minus t naught, I'm just going to use t naught equals 0 here. It is defined this way. It is the derivative of the unit step. So it is d dt of u of t, like that. And it is equal to, well, it's 0 for t less than 0. And it is also 0 for t greater than 0. So that just leaves t equals 0, and for that it is undefined. It is infinite. Okay. Now you might say, well, how useful is something like that? Well, you got to remember this is the derivative. It is the slope of the unit step function. So if I went back and drew the unit step function here, let's say this is u of t, and here is t, and this is the time at which the unit step transitions from 0 up to 1 here. Well, the slope over here on this side, the dt of that, is 0. So the slope is 0. The slope is also 0 here, past t naught. But right at t naught, what is the slope? Well, the slope is undefined. So that's the way that this thing works. Now, if I were to graph the unit impulse itself, right there at t naught, the unit impulse does this. It goes up all the way to infinity, and we illustrate that by putting an arrow straight up. So it's infinite at that point. This would be delta versus time. So it's 0 everywhere else except at that one point. Okay, but here's an interesting thing that you want to remember. Even though it goes to infinity, the area under the curve, in other words, if I were to integrate this, I would find the area under the curve, and the area is 1. So it's 0 everywhere except at t equals t naught. It's infinite at t naught, but it has an area of 1, and that's what makes it useful, so that you can use it in functions like this. Let's say we're going to integrate from a to b, some arbitrary boundaries, and we're going to integrate some function, which is just some arbitrary function of time, any function of time. But we're going to multiply that times delta t minus t naught, and then we're integrating over dt. Okay. Well, since the delta is undefined, in other words, it's 0 at everywhere except at t naught, then this is really the same thing as integral from a to b of this function only at t naught times delta t minus t naught dt. And we'll just plug in t naught there because it's 0. The delta is 0 everywhere except right at t naught. Okay? So that's why we're able to plug in t naught there for the function. Okay, but then when you take the integral of that, remember the integral is the area under the curve, so this just becomes f. In fact, the f of t naught is a constant. I could factor that out of the integral, times the integral from a to b of delta t minus t naught dt. And what is this? What is the integral of the delta? Well, it's just the area under the curve, so it's 1. So this is f of t naught. In other words, what you can do is you can take some function, multiply it by the delta, and then what do you get out? You just get out the function at the place where the delta spikes. Okay, so the impulse function then serves as a method to find this f at t naught. It filters out all of the values except the ones at t. So this is sometimes called a sifting property of the delta there. And yeah, if you stay in circuits or you stay in electrical engineering, you will encounter this probably more than once. If you take a signal processing class, you'll probably encounter it there as well. So when a function is integrated with the impulse function like this, we obtain the value of the function at that point where the impulse occurs. Okay. Now, there is an assumption here, and I didn't say it, but the assumption is that T naught is somewhere between the limits of A and B. If T naught is not in between A and B, then this whole thing is equal to 0. So as long as A is over there and B is over there, and you're integrating between those two limits and the T naught value happens to fall between there, then that's fine. You're going to get 1 out of that, and this is going to look exactly like it does here. Otherwise, it's going to be 0 because you're integrating over an area. Imagine A and B is shifted over here. You're integrating over limits that do not include the T naught, and it's going to be 0. Okay, so that's the delta function. Let's go now and talk about the unit ramp function. Okay, the unit ramp is written this way, R t minus t naught, and it is defined as 0 for t less than or equal to t naught, and it is defined as t minus t naught for t greater than or equal to t naught. So right at t naught, that's where the discontinuity occurs. Okay, that type of function like that is called a delayed ramp. And the reason it's called a delayed ramp is because graphically, if we were to draw that, this is R versus t, and let's say right there is the time t naught, and this is 0 time. The ramp is 0 for all points beyond that, but after that point, then it increases linearly. And it's going to have a slope here of, or a slope that creates an angle there of like 45 degrees. So it's going up linearly, directly proportional to t. So it increases directly proportional to t. And that t naught then becomes an offset. So it's delayed in time. It doesn't start at 0, it's delayed. That's why it's called a delayed ramp. You could have an advanced ramp. That's written this way, R of t plus t naught, okay? And that's equal to 0 for t less than or equal to t naught, and it is t plus t naught for t greater than. I shouldn't say that, I should say negative t naught, like that, okay? It grows, it increases proportional to time as well, but it starts back here, okay? In other words, it doesn't start at t equals 0, it started before, so it's advancing faster. It's started at a time earlier, and it's going to look like that. Again, this is R, this is t, the angle there is going to be 45 degrees, and this is time negative t naught right there, okay? So that's an advanced ramp. Think of it in terms of the time. The time started before t equals 0. Up here, the time was delayed until time t0. So that's the difference between those two right there. We will mainly use this one when we're talking about derivatives and integrals as well, okay? Because the integral of u of t is r of t. That's the relationship between the unit step function and the ramp function here. So we've got these relationships, and let's sort of summarize them at this point. We've got the u of t, that's the unit step. and it's equal to either 0 or 1 for t less than 0, for t greater than 0. And out of that, we've also got delta of t, which is equal to d dt of u of t, like that. And then also we have this relationship, u of t is equal to d dt of r of t. That's the relationship between those two. And we could say this, that u of t is equal to the integral from negative infinity to time t of delta of some variables, let's say delta of x dx. Okay, this one can be derived from this one. So just take this relationship here and solve for u of t, and you're going to end up with something like that. Okay, and then r of t, oh, by the way, the reason that those units are like that is because we want t to be within the boundary. Okay, it could have equally been something else, limit, but we need to make sure that t is within the boundaries of the limits. R of t is integral negative infinity to t of u of x dx, like that. Okay, so those are the general relationships between these three functions that we've learned here. Okay, let me point something out here that maybe you didn't notice. Maybe I should have said it, but this unit step function is going to be either 0 or 1. Now, it is 0 if what's inside the parenthesis here, this is just another way to think about it. If what's inside the parenthesis is negative, if what's inside the parenthesis is negative, it's going to be 0. But if what's inside the parenthesis is positive, it's going to be 1. So think about it in those terms, and maybe it'll be less confusing. It's going to be either 0 if what's inside the parenthesis is negative. It's going to be 1 if what's inside the parenthesis is positive. Okay? So with that said, then, let's do let's do 2 or 3 examples here. So let's say we go from negative infinity to infinity of sine 4 pi t integral t minus 2 dt. Okay, what is that? Well, this is a sifting function now. So it's going to end up being that function, which is sine of 4 pi t, but the t is going to be where what's inside the parenthesis is 0, which is at t equal 2. So this t is going to be 2. So this whole thing is going to end up being sine of 8 pi. When I take the 2 and multiply by the 4, it's going to be that. Okay, so there's the answer right there. Let's do another one. The integral from 0 to infinity of e to the negative alpha t cubed times delta t plus 10 dt. Okay. Now, what's that going to be? Well, it's going to be the function evaluated at the t where it makes what's inside the parenthesis 0. So when is that 0? At t equals negative 10. Okay, so we need to know that this is going to be e to the negative alpha times negative 10 cubed, like that. And that's going to be, the negatives are going to cancel each other, so this is just going to be e to the alpha times 10 cubed. Okay, so there's our answer for that one. Let me stick one more in here. Let's say we got e to the 0 to infinity of e to the negative alpha t, we can make it t cubed again, times delta t plus 10 dt. In other words, it's exactly the same thing. Okay, but all I did is oh, wait a minute. I actually, let me fix this. There. Now we've got the correct answer for that one. But what's this one going to be now? Now it's going to be 0. Now, why is it 0? I made a mistake previously. That should have been a lower limit of negative infinity. That was a mistake. This is the correct answer if that limit is negative infinity. But now that I've changed that limit to 0, notice what happened here. The answer is 0. So both of these are correct as written right now. It's because at t equals negative 10, that's outside the limits. Negative 10 is, 10 past where 0 starts. So it's not going to work. It's going to be 0 because the delta is only defined at one point, and that one point is at t equals negative 10. Okay, or I shouldn't say it's defined at one point. It only occurs at one point at which its value is technically undefined. Okay, one more. Integral from negative infinity to infinity of delta of t equals what? Okay, you should know the answer to that one already. It's just 1. Okay. All right, so we've done a few examples there with the sifting property of the impulse function. Let's work another problem. Let's say we've got a voltage. And let's put some marks on here. This is T, and this is our voltage as a function of time. And I want 10 volts there. I'm going to mark 10 volts. This is 0 down here. And then time-wise, I'm going to say there's 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6 units of time there. And what I want is I want my voltage to increase to 10 volts right there, stay 10 volts until about t equal 5, and then for it to go back down like that. Okay, so it's 0 outside of 1, so less than 1 and greater than 5, the voltage is 0, but right at or right between 1 and 5 seconds, or 1 and 5 units of time, the voltage is 10 volts. Okay, this is called a gate function. All right, and what we want to do is we want to express that voltage right there in terms of singularity functions. So here's one way to do it. V of t is going to equal to 10 times u of t minus 1. Okay, now what's going to happen here is when what's inside the parenthesis becomes positive, which is going to happen at 1, then it's going to jump up to 10 and it's going to stay 10. The problem with this is we're not finished with it because it's going to stay 10 forever until unless we can figure out a way to make it stop at 5. Okay, well, one of the ways to make it stop at 5 is just to subtract off 10 u t minus 5, okay, volts. And that's the function that will cause it to happen, is cause it to increase to 10 volts at 1 unit, then stay 10 volts until it gets here to 5, and then at 5 we're subtracting those two, and it just goes to 0 from there on out. Okay, so you could simplify that a little bit. You could say 10 of u t minus 1 minus u t minus 5 volts. Okay, that's one way to do it. Let's, for the sake of fun here, let's find dv dt. Okay, dv dt is going to be the derivative of this whole thing right here. Okay, well, the 10 is a constant, so we're really just taking the derivative of each one of those unit step functions there. So this is going to be 10 times du dt t minus 1 minus du dt for the t minus 5. Like that. Okay, well, what does, remember what du dt was? Let me see if I can find that. Here it is. Du dt was delta, a t. So each one of these is going to end up being a delta function. So this is going to be 10 times delta t minus 1 minus delta t minus 5. Now, the delta functions only exist at the place where what's inside the parenthesis is 0. So if we were to create the same sort of a graph we did up there, this is t, this is now dv dt, and here at t equals 1, 2, 3, 4, 5, here's what we're going to find. It's going to go up like this, and at 5, it's going to go down like that. So they're going to be undefined at those 2 points right there. Okay. All right. That was just for fun. Let's see if I can find another problem that we might want to work. Yeah, here's a good one. Let's say we've got a voltage function that looks something like this. This is V of t versus t, and let's say from 1, 2, 3. So 1, 2, 3. We've got this at t equal 2, something happens. It's rising up, and then all of a sudden it drops down to 0 again. Okay, so we got this linear rise between 0 and 2 seconds, let's say, but at 2 seconds it drops down and returns to 0. So that's kind of a sawtooth pattern there. Okay, and what we want to do is we want to express that using singularity functions. Okay, well, to express that using singularity functions, there's probably more than one way to do that. In fact, I know there's more than one way to do that. Let's talk about, I don't know, let's talk about 3, 4, or something like that, at least a couple, so that we can figure this out. If you look at this, there's kind of 2 parts to this. There's an upward slope, and then there's the canceling part. But after the canceling part, you gotta have 0 all the way down until infinity at that point. So you could write it this way. You could say v of t is equal to 5 times r of t. Now, why did I do 5? Well, something I didn't write on here is that's 10 volts again. So if that's 10 volts, then what's going to happen is at t equals 0, in other words, when we reach t equals 0, the ramp function turns on and it rises up linearly until it reaches 10 volts right there. Now, the problem is with this, it's going to continue to rise. So we're going to have to add some more stuff out here to cancel it out. But that'll take care of everything between 0 and 2 at least. And it'll rise up with a slope of 5. So rise over run, rise is 10, run is 2, so that's 5. That's where that 5 comes from. Okay. So after 2 seconds, or it's risen up to that. Okay. Then we need to cancel that out. So we could just do something like this. We could say minus 5 r t minus 2. Okay, at that point, then we've got a downward slope. The negative. This is the same function. It starts at t equal 2, but it's got a negative slope, so it's going to go down here. Okay. In other words, let's say let's redraw that. Let's say this is 10, and that's t right there. This is this first one. This is the 5r of t. But then we're doing the second one here at t equals 2. Then it starts doing this. Okay. So yeah, it may be that at 2 it's going to start subtracting off of that, but notice it's not really, because this is a delayed ramp and it's in the negative direction, it's not really going to cancel it, because this function over here has already had 2 seconds of time to get started, when this one only gets started at 2, so it's never really going to subtract it off. In fact, if you took this first one right here and you subtracted off this 5rt minus 2, what you're going to get is something that looks like this. It's going to go up till t equals 2 at 10 volts, but then it's going to look like that. It's just going to level off. So what we need to do is we need to kill this part right here. Okay, we need to get rid of it. And that's up to 10, so we can add this term. How about minus 10, that should be u t minus 2. Okay, volts, and I think that would do it. So minus 10 u t minus 2, and that gets rid of it, okay, and makes it look like this. All right, so there's one way to do it. Okay, this is what we want. We want to replicate that. So let's try and do it another way. We could write it this way. V of t equals 5t times u of t minus u of t minus 2. There's another way to write the voltage. What we effectively have here is this. This is a ramp. And this is a gate. So we've got a gate function multiplied by a ramp function. So this turns it on at t equals 0, and this turns it, subtracts it at, or effectively cancels the first one here at t equals 2. So the gate function multiplied by the ramp function, that's another way to do it. You could, you know, that says 5t. It's not technically, we didn't use the r, it's not technically a ramp, but it is linear with t with a slope of 5. So it is effectively a ramp. We could have written it this way: v of t is equal to 5r of t. Okay, that would be the ramp portion here. But let me show you a trick when it comes to this unit step gate function here. U of minus t plus 2. Now the minus t plus 2, remember this is 0 when what's in the parenthesis is negative. The ramp itself, well, that's just going to go up forever, but we need to control when it starts and when it stops by the unit step. So how are we going to do that? Well, think about what this unit step function right here does. Let's see, at t equals 2, it looks like it does something. So at t equals 2, that's when it's going to transition. So there's 1, there's 2. So 1, 2, let's do 3, 4. Back here's negative 1, negative 2. That's t, and this is u. Okay, well at t equal 2, it's going to do something. Well, what about at to the right of 2? Let's say if that's a 3, that's going to be negative 3 plus 2. So what's inside is going to be negative. In fact, it's going to be negative over here to the right of 2. That means it's going to be 0. So it's not going to exist. Then what about for t equals 1? Well, t equals 1, we've got 2 minus 1. That's going to be positive. So it's going to jump up here to its level of 1. And at t equals 0, same thing. T equals negative 1, we're going to have minus negative. So it's going to be positive all back here. So by adding that negative sign in front and making that a plus 2, we have made a curve that looks like this. That means that it's defined as positive, or I'm sorry, it's defined as 1 before t equals 2, and it's defined as 0 after t equals 2. Okay, but you might say, well, doesn't this part back here, doesn't that play a role? Well, no, because the ramp itself doesn't turn on until t equals 0. Before t equals 0, the ramp is defined as 0. So the ramp is doing that. Multiply by that, the net effect is we end up with, well, I don't have to redraw it. We end up with this right here. Okay, so there's another way to do exactly the same thing. And you're probably going to discover that these things pop up from time to time as we go through some of our problems later on. Let's do one more. Let's say we got V of t, and V of t is 15 delta t minus 2 millivolts. And this is for an inductor. Let's say this is the voltage across an inductor. In fact, the inductor has an inductance of 10 millihenries. We're going to assume the passive sign convention here, so we don't have to worry about sign. But this is the voltage across that inductor. Okay, let's say that I want to find the current. Well, we know that V equals L di dt. So I should be able to get I out of that. And I is going to be equal to 1 over L times the integral V dt plus I at 0. And we will assume for the sake of this problem that there was no initial current passing through the inductor, so this is really 0 here. Okay. Well, what does that mean? That means the current is going to be 1 over L, it's 2 o'clock, times the integral negative infinity to infinity of 15 delta t minus 2 millivolts dt, like that. Okay, that looks like a shifting function, doesn't it? In other words, this is going to be equal to 1 over L times 15, which is just the constant here, evaluated at t equals 2, and that's what I is. Well, let's see, L is 10 millihenries, so this is what, 0.01. So it's going to be 1 over 0.01, the reciprocal, since that's 1/100th, it's going to be 100 times 15. Because there is no evaluating it at t equals 2. 15 is always 15, regardless of what t is. So that's going to be 1500. Now we got to be careful here because we have units of millivolts there. So 1500 millivolts. So I equals 1500 millivolts. Okay. Or we could say 1.5. What am I doing? Millivolts. When we integrate it though, it's going to be amps, so milliamps. So that's milliamps and that's amps. Okay. Now that we've fixed that problem there, I have to warn you, we're not finished. We're not finished with this because this says I is equal to 1500 milliamps for all times, or it's 1.5 amps for all times. We need to realize that the voltage is that. Remember this. du dt is delta. Okay? t, like that. So if we were to rewrite I as 1.5 u using the same t minus 2 as we did up there and say that that's amps, well, that's a much more correct answer. And the reason is because if you take the derivative of this, remember V equals L di dt. If you take the derivative of that I, we're going to end up with L times 1.5 times du dt, t minus 2. Okay, so what is that? That is just the delta of t minus 2, so it's going to be L times 1.5 times delta of t minus 2. Okay, and the L is 0.01, multiply by that, and you end up with 15 millivolts for your voltage then. Okay, so the I, you need to consider that. When you work a problem like this, you need to realize that if there is some sort of singularity function in the voltage function you're given, there's got to be some sort of singularity function in your final answer. So keep that in mind. That's probably it for singularity function. That's about all that we'll do at this stage. And later on, we will actually begin using these in some of our problems. Okay, we're done for the day.